Okay, guys, so I think that we need to start. And we are discussing about, yeah, oh yes, I'm in mute. So we are discussing about externalities. As we say that we have both positive externality and negative externality, and we talk that why the market failed and what are the solutions that government should take, and we come with applying fees, standard, and also refundable, recycling. Now we are going to talk about stock externality. Means that an accumulated result of an action by a producer or consumer which, though not accumulated or accounted for in the market price, affect other producer or consumer. You can have this, like for example, global warming. Actually, the global warming is a byproduct of the stock externality. When we start, polluting, when we consume, we have a negative externality to the environment, of course, because we are emitting, we are producing pollution or CO2. Greenhouses also, that so many greenhouses they use for agriculture and that produce CO2 emission or gas. So it is an accumulation of years and years, 100 years, 200 years, 1,000 years. Of course, it's not 1,000 because we start polluting with one start of the 20th century in 19 something like that. So almost 100 year. So this is an accumulation of that external or stock externality. So how does the stock of a pollutant change over time? So here is going, or we are going to have how basically we count or calculate this stock externality. So remember, we always have a base year, right? Year to start. For example, as I say, 1900. From there, we start polluting. So with ongoing emission, the stock will accumulate, but some fraction of the stock, we call it lambda, will dissipate each year. So means that dissipate means that when we waste or throw away something, right? So assuming the stock start at zero, means that we have zero, what we call it, externality or emission, right? In the first year, always in the first year we have zero. Then the stock of pollutant, or we call it S, will be just the amount of that year emission. So how much we pollute in that year, that will be the stock, because that is the base of the year. So in general, the stock of any year is given by the emission generated that year plus the non-dissipated stock from the previous year. The previous year that we also suppose have a pollution, but we did not throw away or waste or dissipate. So that is the general equation. For the 1 year, we say that the stock of pollutant is S1. There is the mouse. Okay. You can see my mouse moving. Okay, now okay, I can see it. So S1 equal to E1. Okay, so the stock of pollutant will be the amount of emission. E is emission of that year. But in the second year, for example, we go to the second year. The stock of pollutant will be equal to the emission that year. So E1 plus 1 minus lambda, which is the fraction of the stock that will be dissipate times the stock of the previous year, which is, let's say in here, year 2, stock of year 2 equal to emission of year 2 plus 1 minus this fraction of stock times the stock of year 1. Then, if third year, we will say S3 equal E2 plus 1 minus lambda S3 minus 1, which is S2. S2 we already have, which is E1 plus 1 minus lambda S1. Then we go for E4, E5, E6. This is mathematics. I'm not going to show here how we get it. Then after, in mathematics, when we have N, if emission are at the constant annual rate, we assume that it is in a constant rate. That means the rate is not increasing or decreasing, it's constant, which is E. Then after N years, 100, 200, infinity, right? The stock of pollutant will be Sn, and for that particular year equal to E times 1 plus 1 minus lambda plus 1 minus lambda square plus 1 minus lambda n minus 1. And in mathematics, if this n becomes in infinite number, then this equation will be E divided by lambda when we go for the infinity. So this is how we calculate the stock externality. For you, no need to understand how we get this if you don't know mathematics. If you know mathematics, you can try it yourself. If you don't know, remember this is for every year. If n number of years go for infinity, then the stock will be E, or the emission divided by lambda. Okay, so now we have an example here, a numerical example, which is table 18 and 1. So to understand this concept that I just now show in equation, right? Now we do it empirically. So we can make this concept of the equation more understanding with this example. We suppose that there is no government intervention, and we have 100 units of a pollutant that will be, this is emitted to the atmosphere every year for the next 100 years. From now, let's say 2020 until 100, that means 2120. Okay, in the table start from 2010, that means 2110. And the rate at which the stock dissipates, which is lambda, equal to year 2. Okay, it shows that equal to 2. Then we have also the stock of pollutant is here. Where is the stock? Okay, start with 100, then become increasing 199, then 296. Following the formula just now we done. Then when we go to 100, we will get X from 2009 0, for example. Now, then 2010 become 100. Then in 100 year become 4,357 units. Okay. You ask me how we calculate that, I will tell you using this formula. This is 100. So we are going to do 100 times here. Okay? Okay. Now, what happened if goes to infinity? We say at infinity equal to E divided by lambda. Lambda here is 2%. Huh? I think it's not written in the table, but it is 2%. From here we can see, yeah, 0.02. So E, it is 100. It says that we pollute 100 unit per year, divided by 2%, which is 0.02, and equal to 5,000. So at infinity, we will have the stock or stock externality will be 5,000. But again, here, also in the table, if you can see, we have how much the damage for each year and how much the cost for each year, what is the net benefit for each year. So we suppose that the stock of pollutant creates economic damage. This damage in terms of the people get sick because of the pollution, and when people sick, usually we cannot work very well. Most of the time we take an MC. Also at work we are not productive, so the productivity will increase. And in order to treat those people, government need money. So this is all cost. So this cost equal to 1 million, for example, per unit, we assume. So if the total stock of pollutant were, let's say, 1,000, if the stock, for example, were 1,000, so the economic damage will be 1,000 times 1 million and become 1 billion. And if, let's say, the annual cost of reducing emission of 15, let's say 15 million, we have emission of 15 million that we need to reduce. How much the cost? The cost will be 15 million times 100 and equal 1.5 billion. Okay. So in order to reduce the emission from 100 unit to 0, so we will take how much the total cost, 100 times 15 million for each unit, and we have 1.5 billion. So every year to reduce this 100 million unit of emission, then we need to spend 1.5 billion at the damage cost of 1 million per unit. Also, sorry, 15 million per unit. But the thing is that, is it that really efficient or make sense to reduce the emission to 0? So in order to answer this, we must do the cost benefit analysis. And if you remember, in microeconomic 1, you have studied about the present value, because we have to discount our money. If I want to spend 1 million now to repair something, that things that I repair, I get the benefit after 10 years. So if you are a really good manager, you have to discount your money. So usually we discount it by the interest rate. Means that 1 million now, after 10 years, it is not 1 million. If the interest rate is 10, so it's become more than 1 million. Depend on the interest rate. So in order to see if our reducing emission to 0 is make sense in economic sense or no, we need, as I said, to compare the present value of the annual cost of this 1.5 billion with the present value of the annual benefit resulting from the reduced stock of pollutant. So if the emission were reduced to 0 starting immediately here, then the stock of pollutant would likewise be equal to 0 over the entire 100 years. From here to here will be 0 because every time we are going to reduce this emission or pollution. So we will have 0 stock. And therefore, we can say the benefit of the policy would be saving the social cost associated with the growing stock of pollutant. So what will be the benefit if every year I'm going to reduce the emission by 100 units and spending 1.5 billion? I tell you that the benefit will be the social cost that supposed to be, exist or harm the society. So in this table, we will, if you can see that the annual cost of reducing emission from 100 to 0, then we have also the annual benefit from averting damage. This is the cost to reduce emission to 0 every year, 1.5 billion. And this is the net benefit or the social benefit, or what we call, we have the annual benefit from averting the damage. And the annual net benefit means that the annual benefit net of the cost of eliminating the emission. So what do you expect here? If we see the annual net benefit here, 1,400, then become in the first year, then become, see, in minus means that the cost is greater than the benefit. The first year, second year, the cost greater than the benefit. The third, also the cost greater than the benefit. Until we reach somehow, I don't know where, maybe in 5 years, in 10 years, in 50 years, when we have the benefit is greater than the cost. For example, here at 100 years, we see here the benefit is 2, the cost is only 1.5. If it goes infinity, the benefit is 3.5, the cost is only 1.5. So as you expect, the annual net benefit is negative in the early years because the stock of pollutant is low, and the net benefit becomes positive only after the stock of pollutant has grown, maybe after 10 years or 20 years or 30 years. So this is tell you that you as a policymaker, at the beginning, it does not worry you, or you do not consider at the beginning you are losing money. The cost is more than the benefit, because later, after 5 years or 10 years, then that become in the opposite way. And if it is an infinitive, actually you are going to gain money. Put it in the business side. You open a new business. At the first 5 years, you lose money. After 5 years, you will start making money forever. So for the 5 years, maybe you lose 1 million. Then after that, maybe you are gaining every year 2 million or 1 million. So it is a beneficial business. You lose at the beginning, then after you will benefit or win forever. And this is what happened here. So you as a policymaker, you should go for that. It makes sense for you, because first you will lose at the beginning in the few years, then after you will gain forever. So to determine whether policy of zero emission makes sense, we need to calculate, as I say, the net present value of the policy. And in this case, the present discounted value of an annual net benefit that we showed in previous table, and let's assume that the discount rate is R, or the interest rate. Therefore, we will have the net present value equal, this is cost, minus 1.5 plus 0.1 plus minus 1.5 plus 0.198 divided by 1 plus R, interest rate. Okay, those numbers are here. 0.1, the damage, 0.18, 0.29, and continue. Okay, so plus minus 1.5, because you see here, all the cost is 1.5, 1.1, 1.5. Then until you reach 100 years. So n minus 1, that means 100 minus 1 is 99. So in order now to calculate this, the net present value as a function of the discount rate, it also shows how the net present value of a zero emission policy depend on the dissipation rate, lambda. This is dissipation rate. This is calculated by the dissipation rate, right? And also it is based on the interest rate. So we can see here, this is the discount rate, and this is dissipation rate. We assume from this formula we calculate this, okay, yeah. So when the depreciation rate is only 0.01, and you can see a discount rate 0.01 positive, 0.02 positive, 0.04 positive, 0.06 negative, that's mean above 0.6 and above is negative. So when we say that when the discount rate is higher, then it does not make sense. Same here. If the dissipation rate increase from 0.1, let's say, to 0.4, then you can see the positive sign started only from 0.4 only. So we can say this policy is depend on the dissipation rate lambda. If lambda is lower, the accumulated stock of pollution will reach higher level and cause more economic damage, and the future benefit of reducing emission will be greater. So again, it is based also discount rate. The net present value of eliminating emission is much larger if lambda is 0.1, is 0.1, is 0.6. If it is 0.4, it's 0.4, 0.4, the discount rate. And much smaller if lambda is 0.4, correct? Also, this can tell you the reasons why countries in the world always talking about we should put more effort to reduce the green houses gas, and they need to dissipate as much as they can, because actually the stock of greenhouses gas dissipate is very slow or very low, which is equal to 0.005. Yes, since lambda is 0.005, which is above here, therefore the damage is huge. And if you don't, those countries take action, therefore the future is uncertain or problematic. So now we talk about social rate of discount. You should know that when those in policy makers or policy makers, especially in the environmental policies, when they tackle those externalities or emission, they always regard of these stock externalities. And designing these policies is not that really easy, because there are other factors that need to be considered. For example, if you want to reduce emission, yes, you can, but what about economic growth? Reducing emission means that reducing economic growth because we need to reduce production. And that one make people less wealthy and maybe increase poverty rate. So we come to the expected rate of the real economic growth. With rapid economic growth, the future generation will have higher income than this current generation. They consume more, pollute more. The extent of risk aversion of a society as a whole means, what does it mean? Risk aversion, I think that you know it, you have studied in Microeconomics 1. When people are, or people tendency to prefer outcomes with low risk or uncertainty rather than high risk or high level of uncertainty. So if the marginal utility of income is decreasing, that means they are risk averse, their utility from an extra dollar will be lower than the utility of to someone living today. So that's why future benefits provide less utility and should those be discounted. So in the future benefit, we need to discount, we need to incorporate the interest rate of that. And then you have the rate of pure time preference for society as a whole. In addition, even we expected no economic growth, for example, at all, economic is not growing, people may simply prefer to receive a benefit today than in the future. Therefore, you will consume more today than in the future because the rate of pure time preference, or people as they call it. Usually, people always prefer to maximize utility today than the future. If I ask you, also you do that. So these kind of three things that need to be counted in there. Then we have this theory that we are going to explain it here in a graph, what we call Ronald Coase theory. It says that how problem created between two parties, let's say producer and consumer, producer of, let's say, a steel firm, last time we talked about, which is producing or polluting the river, and the fisherman, for example, between them. So those problems between them can be solved. Fishermen, they will say to that firm, hey, you are polluting the river, I cannot catch fish, I will not have any food to eat, or I don't have water to drink. The firm also need to throw the waste in the river to produce and to make profit. So how we solve that problem based on Donald Coase theory? This how problem created between the two parties because of the externalities can always be solved through negotiation. So these two parties, they sit together and negotiate, but there is a condition. This should be as long as the negotiation are costless. That means that the cost of negotiation are zero. I will sit with you, student, with lecturer, we solve problem. For example, I didn't attend the class, then no need for us to go to the attorney and bring the lawyer. So we settle this together. That is costless, right? And the law assigns the responsibility for the damage to one of the two parties. That means that one of the two parties, they must have the copyright or property right of that river. If the fishermen, they have property right to clean the river, then they will tell the firms, hey, we are going to clean the river, you need to pay amount of money, then negotiate about it. So transaction cost, as I say, the cost of negotiating and enforcing an agreement between the two parties, there when we have transaction cost, that's when we come to the legal. There is a lawyer. So do not put it in your mind when we have this problem of negative externalities in big corporate firms that it will be less like 1,000, 2,000, like we are going for a divorce case. No, no, no. That is very costless because the clause of the writing of those clause and those conditions is very tough and need to very high skilled lawyers. So you know the fees will be, or legal fees will be very high. And property right that we are talking about this Ronald Coase that he say one of the two he must have property right. That means the legal rules regarding what individuals and firms can do with their property. You have property right, and government it give you that property right. Will tell you, if for example give it to the fishermen, it will tell them that what they should do with this property right and how they clean the river, what the benefit they get from it, how they expect, and vice versa. If they give this property right to the firms, and they will ask the firm how much to pollute, how to pollute, and how to negotiate whatever. So by assigning property right to one of the two parties in a dispute over externalities, all problems of externalities could be solved efficiently. This based on that theory. Now, of course, you would not understand it because in that, what we say, theoretical perspective. So what we do is, let's go and have, this example. So assume that we have this lumber mill owner and that pollute, as we said, polluting in the river. And also we have the shared valley community, which is, we assume them as a fisherman, that they are benefiting from the river. So why is the externality problem? Lumber mill dams a maximum of 150 tons of pollution into the river. And the marginal benefit of this company, the marginal benefit of dioxin abatement for nearby community, we will be the marginal benefit of abatement, which is 600 minus 4 ton. This for the marginal benefit of abatement for the community. So what is the marginal cost of that abatement that this lumber mill will bear? Is marginal cost of abatement is 2T, which is 2 ton. If T is 100, that's 100 ton. That means 2 times 100 is 200. So here, if you still remember, we say that when these two parties come to, we say, the efficient level, we will have the socially optimal level of abatement, where the T equal to the marginal benefit of abatement equal to the marginal cost of abatement. And if we see here, we draw, this is the marginal benefit for the community, 600 minus 40. If T 0, MBA is 600. If MBA is 0, so 40 equal to 600. That means T equals 600 divided by 4 and equal 150. And this is the cost. We say MC equal to 2T, T equals 0, MC 0, T equal 10, MC 20, T equal 50, MC is 100, T equal 100, then MC equal to 100. So what is the efficient level? We say that when these two are interacted at this level, where we abate 100 units at the cost of 200. Okay. Now, how these two, based on this theory, they are going to negotiate? So we have scenario 1, which is property right to the river assigned to lumber mill owner, which is the polluter. This is the scenario, means the property right of the polluter. So community may feel helpless because why? The firm can dam the toxic or pollution into the river with impunity, but the community still has an option. Since the property right government given to the polluter, so the community, they cannot stop her. What they do, they will call that firm, they say, oh, let's sit together. Let's negotiate. So they will come to a negotiation. So we have a feasible option here. So the community offers mill owner or the firm $200 per ton. So in order to abate at 100, so they give 200 for each ton. Therefore, this firm will have revenue of 100 times 200, which is 20,000. So the firm will have 20,000 as a return. So this is profitable to the firm. Why? Because by eliminating the first 100 ton, it will cost her how much? 100. It will cost, actually, this is the cost. 100 times 100, it costs her 10,000 K. Okay. Which is area C, right? We say the cost is below the marginal cost. So from this 0 to here, 100 times 200, 20,000 divided by 2 because triangle. So it will cost her 10,000. And how much revenue? 100 times 220,000. The cost 10,000 and the benefit will be this B, 10,000. So 10 plus 10, 20,000. So by giving 20,000 to the firm, what is the marginal benefit for those people? Is below that until here. So this will be the benefit, which is 600 minus 200, which is 400. 400 times 100 is 40,000, divided by 2, 20,000. So they give 20,000 and they benefit 20,000. So win-win situation. Again, the firm will not reduce emission or will not abate more than 100 tons because the marginal cost for that will be more than 200. You see, until here is 200. If go more than 100, the marginal cost become more than 200 and the benefit for that firm will reduce. So this firm will not agree to abate more than 200. So as I said, community will pay 20K. In return, we receive this area A, 20K also. And therefore, both the firm and the community are better off, and the final result is social efficient. So if, let's say, we have an unfeasible situation, if, let's say, below 200, which is below, sorry, 100, which is 50. So if those people give this firm only 50 units, or the firm to reduce by only 50 ton and for a payment of only 5K, 50 minus 0.50 times 100, so it is 50,000. Oh, sorry, 5,000. So it benefit 5,000. Okay, that is the cost 2,500 and benefit 2,500. So the community here, they realize that the marginal benefit for additional abatement, which is greater than $100 that they give, actually give them more or additional benefit. So they offer to the firm to reduce more at a higher price. They keep increasing from what they give only 100. When they give only 100, the firm abated only 50 based on that cost, right? So they will start increasing. The more they increase, the firm abate more until they reach 200, and we reach the social equilibrium or the efficiency. So again, we can say we reach the socially efficient outcome also. Let's say if the firm start giving only 100, the community give to the firm only $100, not $200 per unit. The firm will abate only 50. Then those people, they keep increasing because they get more benefit until they reach the social efficient level. Now, this is scenario 1. Scenario 2, we assume that the property right to the river assigned to the community or the victim, fishermen, or the community or the people, they have the copyright. So community can completely ban the dumping of the firms or the pollution of the firms. And in this case, what happened? The mills dump or the firm, the total cleanup cost is much higher because it must clean everything, not here, but everything. So it will be, this is 100,000, the cost, plus this is 5,000. You can calculate it, 200 times 100 divide, sorry, this is 200 minus 0, so 200 times 50. 10,000 divided by 2 because triangle 5,000. This is also, this minus this, 150 minus 100 is 50 times 200. 10,000 divided by 2, 5,000, and this is equal to 300 minus 200, which is 100. 100 times this minus this, that's me 50, which is 5,000. 5,000 divided by 2 is 2,500. So we have 2,500 here. We have 5,000 here. We have 5,000 here. 10,000. So how much all? 10,000, 15 and 15, 10,000, 20,000, 22, and 500. So 22.5K. This will be the cost. So the firm, in this case, the cost is very high. Before it's only 10,000. Now it must pay 22.5K. So what happened? The firm will call the community for discussion. Okay, let's solve this problem. Assume the first one, infeasible option. So below 200, the cost, right? Example 100 here. Profitable for the firm to reduce by only 50 ton at 100 for a payment of 5K is to the community, the benefit. So community realized that the marginal benefit for additional abatement more than 100, you can see here, the blue one, would make additional offer to the mill to reduce more and higher at higher price. So they offer more and more and more and more until reach the unit 200 price, and marginal benefit will be this 10,000 for abating 100 unit. And here we will come to the socially efficient level. So the community can completely ban, as I say, sorry, the scenario, second scenario, you say, sorry, yeah, the cost is 22.5 here, K. Okay. And the fishermen have the property right. So we say now, again, I just confused just now. Here the firm will offer to pay 200 per ton dumped into the river. The firm will give 200 per ton to dump. So the firm will give until 100 ton here to reach this equilibrium. It will dump 100 ton and it will give 200. So this is the cost and this is the benefit. So rather than the profit for the mill will be eliminated. So we have the area C as cost for the firm as previously one. So rather than paying for 20K to community for the right to them, those face 100 ton. So it just abate and it costs her only 100 or 10K, 10,000. It pay 20 for each, then 20 times 100, it must pay 20K. So better to abate. So the firm will offer to pay 10K area D plus E, also cost, right? So it pay that to pay this to the community and get the right to dump the remaining 50 tons. And this is still costly than cleaning up those 50 tons because it will have this plus the cost to clean. So 10,000 plus 2.5, 12,000.5. So it is costly also. So community happy to accept the offer since 10K payment from the meal or from the fare is greater than the total benefit of only 10K of this plus this or D that offer an E, right? So what happened now? The firm offers below 200. For example, you offer 100 per ton to reduce only 50 this. So here community would permit the firm to dump only 25 ton. Why? So that receiving payment 2.5K from the mill, 25 ton here, they will receive only 25 or 2.5, sorry, 2,500. The extra 75 ton, because the marginal cost is more than 100. So it is better for the firm to offer higher price to the community for the right to them until reach 200. Keep increasing until reach 200. Then also reach to the socially efficient level. So this is the negotiation. So depend which party holds the property right, then only we can see the scenario. So this is all explanation scenario we have done. So now we come to this conclusion as a summary for the Corsi theorem. If transaction costs are zero and legal property rights are clearly defined either to one party or the others, bargaining between the two parties will always result in an efficient outcome. So we continue. So we say the previous example just now we have discussed about the negotiation. We assume that the transaction cost is zero. That means the negotiation happens in a very amicable way, a friendly way. We sit together and we discuss. There is no lawyer, no legal fees. But actually, as I say, in corporate life or between countries, there's a conflict. Those things is not easy to be settled with friendly negotiation. In real world, negotiations are rarely cost-free, and always we have legal fees involved. So the Quasi theorem may be invalid in achieving economic efficiency due to a non-zero transaction cost, as is assumed, and the existence of asymmetric information between the community and the mill. Some information is not really well known to one side of the party or both of them, and likelihood of the firm going bankrupt if the community owns the property right. So the second scenario, we say that the property right goes to the community. In this case, the firm will bankrupt because the community will not allow her to dam the pollution in the river and therefore cannot produce. And if they allow her, they will charge very high, where the marginal cost will be greater than the marginal benefit of the firm, and therefore the firm will bankrupt in anyway. So now we suppose that the firm or the mill firm has the property right to the river. So it is difficult for the thousands of the members of the community to negotiate with the firm or the owner of the river because the property right for her. Community therefore has to hire an attorney, paying a lawyer fee for $600 or $60 per ton abated in the manage to be, or if he managed to obtain from the mill or from the firm. So by paying this $60 per ton, therefore the marginal benefit for the community will reduce by $60 per ton, and therefore the new marginal benefit will be 600 minus 60 minus 40 and equal to 540 minus 40. So the community no longer willing to offer $200 because their optimal level of abatement will reduce from 100, and we can see it here in this graph. This is the original marginal benefit. The marginal cost will not reduce. So the new marginal benefit is reduced by 60. So from here to 540, and we'll have here. So the new equilibrium is at 90 units, and the firm will offer only 180. So the firm will offer only $180, and while the mill or the firm agrees to reduce only 90 tons. So therefore, in this scenario, before, when there is no transaction cost, we have the firm will abate 100 and the community will pay $200 per ton. So when there is transaction cost, now the new equilibrium will be here at 90. So the firm will abate only 90, and the community members are willing to pay only 180 per ton. Therefore, this triangle in orange color is the deadweight lost, the community lose. So here we can see the deadweight loss equal to the orange shaded triangle. The higher the legal fee, the larger the deadweight loss. You can see. For example, if legal fee is 100, therefore this is reduced to here 500, then comes here, then become the new equilibrium is only here at 80. So we will have more deadweight loss. If the fee is, let's say, 200, then become to 400 here, and will be here. This is will be here at 70, will be the new equilibrium. Then this will be the deadweight loss. So the higher cost of the legal fees will generate higher deadweight loss. Now we talk about the common property resources. So we have this scenario or characteristics. The common property resources when everyone has a free access to the resources and likely to be overutilized because any one of us can have an access. For example, in air and water, fish and animal population, minerals. We take an example. We have a lake, for example, a lake where people fish. This lake in Kampala is made by Kampala. You can see people fish there, right? Now let's assume that so many people goes there because no one can use it. What happened? It will be overfishing and the number of fish will be reduced. So we consider a lake where people fish. Each fish person take fish up to the pond where the marginal benefit to them equal to the marginal cost. In that way, for example, if I go to Kampala Lake, my marginal cost is my time. So how much I'm going to fish when I equate my marginal cost equal to the marginal, benefit of that fish. So there is no reason that anyone of fisher person take into account how their taking fish affect others' experience. So when I fish so much in order to balance my marginal cost or my time, I will not consider the negative impact or the negative externality that I produce or impose to others. For example, when the fish reduces, some type of the birds will not come because when there is no food, those birds are usually to come there and catch fish to eat, they will not be there. So people, the negative externality, people, they will not enjoy the view, for example. So the private costs underestimate the true cost of the society. So more fishing reduces the stock of fish automatically, and therefore, which is less is available to other, and too low for the stock will completely deplete the fish one day, because the fish will not reproduce itself since it is too low, catching all the fish that's supposed to be reproduced, and after they catch the small one, then it will be depleted. Too many fish are caught, then therefore it will be 100% depleted. But let's say in this figure here, this figure illustrates the situation. Suppose that because of the catch is sufficiently small relative to the demand, fishermen taking the price of fish as given. Okay? And means that supply and demand, competitive market. Suppose also that someone can control the number of fishermen with access to the lake. Government say, okay, the Kampar, Bandar Kampar, what we call it, Majlis Bandar Kampar, we tell someone, okay, we will give you, you control that lake. We need only 10% to fish per day there, not 100. So therefore, the efficient level of fish per month or per day will be at here, F star, because the person who control will consider the marginal social cost and still to produce at fish competitive market. If everyone come, we produce here. So we control, we produce here. The marginal benefit is the price taken from the demand curve. The marginal social cost shown in this diagram includes not only the private operating cost, but again also the external cost or the social cost of depleting the stock of fish. So now we're going to compare the efficient outcome with that, with what happens when the lake is common property. That means there is now someone considering or to control, to consider the social cost. So in this case, the marginal external costs are not taken in consideration, and each fisherman fishes until there is no longer any profit to be made until the fish finish. So when only F star fish are caught here, the revenue from fishing is greater than the cost. Okay? And there is a profit to be earned by fishing more. Here, see? When we fish more, okay, until we reach here. This is the cost. So when here, revenue, this revenue, the blue, this is the cost. So revenue more than the cost. So there is room to fish, 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 because now we say anyone can enter. There is no one to control. Huh? So public property. So come, fishing, fishing until reach FC. So everyone will fish, 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 and reach point FC, and there we will have the private cost equal to the marginal benefit, MB, and they will stop. They will not fish more than FC because why? The cost, marginal private cost, will be more than the marginal benefit, and increasing one unit of fishing after FC actually will consider losing money, not making money. So what is the solution? I will say in private ownership. So when we give an owner this scenario, just now I explained, the owner will set a fee for the use of resourceful, with the resource equal to the managerial cost of depleting the stock, or that fee is actually equal to the external cost or the social cost that resulted from fishing. So fishermen will no longer find it profitable to catch more than the efficient amount, because here the cost will not be this. Since we add a fee, this will be the cost, marginal cost. So they will no longer fish at that point when the private cost equal to the marginal benefit, but they will fish somewhere here or here until we reach, depend where it sets. So we say fishermen will no longer find it profitable to catch more than the efficient amount of fish. It is often the case that private ownership is not possible. The government steps in. So, for example, sometimes, for example, in this lake in Kampa, nearby Yota, it is not possible that you put someone to control that, right? Because actually it's for everyone's public property, right? You cannot give it to private. So here now government, it must come and regulate. So, for example, we have this example in crawfish fishing in Louisiana in United States. Crawfish has become very popular in restaurants. People, the demand is very high. As a common property resources, too many crawfish have been trapped, causing the population to fall below the efficient level. Means that the reproduction become less and less. Finding the efficient crawfish catch, where the F is the crawfish catch in millions of pounds per year, and C is the cost in dollars per pound. So we have, for example, the demand equal C, the cost equal to 0.401 minus 0.0064 F. F is the crawfish catch, C is the cost. Marginal social cost, C equal minus 5.645 plus 0.6509 F. Private cost equals C equal to minus 0.357 plus 0.0573 F. And the efficient catch, we must have when the marginal benefit, which is D, the demand equal to the marginal social cost. And when this equal to this, we will find F equal to 9.2 million pounds. So we do it here. Okay. So in this figure here, we design or we draw those one. So if private cost, if we compare each one privately, then it will be the private cost or marginal private cost with the marginal benefit is the demand. So it will be at 11.9. But we say when in social efficient, when the marginal social cost with the marginal benefit, which is here at 9.2. So there is a relatively simple solution to the common property resources problem. Let a single owner manage the source. Okay. But we say in this case, government, or it is difficult for a private to give him control over something which is public property. So government here need to find or intervene. So we took that example of crawfish. We have designed this based, as I say, on these equations, and we found an equilibrium at 9.2. So marginal social cost intersect with the demand or the marginal benefit at 9.2, and the private cost intersect with the demand at 11.9. How we get that? You get it from here. Private cost intersect with the demand. This equal to this. C equal to C. This equal to this. Then we will get 11.9. So here the efficient crawfish catch of 9.2 million pounds, which equate the demand to the marginal social cost or the marginal benefit equal to the marginal social cost, and the 11.9 million pound is determined by the equating the demand of or to the private cost or the marginal benefit and the marginal benefit with, or the private marginal benefit with the marginal cost, which is 11.9. So this triangle now, this, and this, is the figure measures the social cost of free access. Because socially, suppose we produce here for the efficient, but if we give it to everyone, then fishermen will produce at this level, then will be the social cost for the free access. So this figure represents the excess of the social cost above the private benefit of fishing, sum from the efficient level, where the demand is equal to the marginal social cost, to the actual level where the demand equal to the private. So in this case, the social cost is approximated by the area of triangle with a base of 2.7 million pound, or you can calculate it 11.9 minus 9.2 times 2.1 minus 0.325. Then this is all divided by 2. So this is, we get around 2,369,000 something like that. So you have to know that by regulating the pond or the lake, we're limiting either access or the size of the catch, this social cost could be avoided. So how we are going to reach this 9.2, as we explained previously, either we limit the number of people to access to the lake. So we put a guard there and we ask him, okay, count for us. Every day only 5 they enter to fish. First come, first serve. Or second, limiting the size of the catch. So once the catch reach, let's say 1,000 kilograms per day, we will stop fishing, we close. Everyone go out from the lake. So whatever more suitable government can make. So you can see this is how usually we consider the external or negative externality in our market equilibrium, and how the negative externality actually produce for us or generate for us cost to the society or the deadweight lost. I hope that you understand the concept. Thank you very much.